And so, how do we compare forward backward versus Viterbi? We've talked about this before, but just to reiterate, the forward backward algorithm, or just the forward algorithm, the backward algorithm does everything backwards, sums over all possible paths that end in each of these tokens of length, of whatever length you're computing. The Viterbi algorithm only keeps track of the best possible path, right? So you use the forward algorithm to compute marginal probabilities, and you use the Viterbi algorithm to compute the best single probability sequence. So just to summarize what we've seen today, for training CRFs, the optimality of, it has a similar optimality condition as HMMs, right? But you have to match frequency counts in this format, and this requires gradient descent, right? If this number is bigger than this number, then you want to tune your model such that this number goes up. If this number is smaller than this number, you want to tune your model parameter so that this number goes down. And you're going to do that for every parameter of your model. Yeah?
So when are CRFs used over anymore? If they're not better for predicting, right?
They are better for predicting. They're discriminative models. Well, in fact,
I thought generative models were supposed to be better.
Generative models are better if you want more flexibility in your model. Because they model the joint distribution of P of x comma y. You can make any query, like I can ask P of x given. Conditional random fields and logistic regression cannot answer P of x given. Right? If the only thing you care about is modeling P of y given x, logistic regression is better than naive Bayes in general. Conditional random fields is better than hidden market models in general. Yeah.
So when would you use HMMs?
So you would use HMMs if you want flexibility in what you want to use the model for. HMMs can generate new samples. HMMs is a full model over the entire joint distribution of your data. So it's an approximation of your test distribution, right, according to your model assumptions. So you can draw samples from it. You could marginalize out over missing values. Right? If you're missing an x, you can marginalize out that x in case you have the joint distribution. You can't do that for conditional random fields.
So would it ever make sense to use HMMs to generate more samples and then run all that for predictions using conditional?
To use HMS to generate training data?
Like take more training data.
I like bootstrapping. Kind of, but you're bootstrapping in a weird way. I've never heard of that before. I don't know how to answer the question. My gut should not be trusted at all. Should not be trusted. Tells me that that's probably a bad idea. Because HMM makes simplified assumptions that is not what you want when your goal is to just predict y events. Yeah.
So it seems like you didn't do any structural assumptions for CRFs.
Well, you make the same structural assumptions of just the scoring rule is just pairwise transitions and pairwise. It's the same structural assumptions, right? The scoring rule decomposes multiplicatively into pairwise transitions of tag,
yeah,
and emission, and then not emission, but association of tag of observation.
So like in HMMs, we did a structural assumption of the first order coding process, and then we know that our model actually is modeling the whole joint distribution.
That's right.
Now here, there's a similarity in the splitting to the Markovian distribution, but
we're not modeling a direction, if you will.
exactly, we're not modeling it directly. So is there something which says that CRFs work good for Markovians, especially because they kind of inherit the structure? Or do they work always? Do they work the best for Markov processes of first order?
I'm sorry. Do they work the best over?
Yeah, do they work especially well for Markov processes of first order, or can you use it also for other processes as well?
Yeah, you can do second order CRFs.
Oh, but then you have to use second order.
Like three times.
Okay.
If you believe that the transitions have second order dynamics, that you cannot model them well using first order dynamics, then you have to use a second order model. If you believe that the second order dynamics are negligible, then you can use a first order model. right, the CRF scoring rule, I mean, if like, let's see here. Oh my goodness. Okay, so the CRF score rule basically says, I want to make the best possible prediction given an X, the one that maximizes the scoring rule, right? This score rule basically says, I associate this token with this word, with this score, and I associate this token transition with this score. And if the actual prediction you need to make in order to model it well, you need second order transitions, so you're not going to capture that with this.
So, like last week we said that if we use HMM to like train tagging sentences, it can, I mean the same thing can be used to generate sentences.
That's right.
But here we can't
No.
use it.
No, it's not a generative model. No. That's one of the limitations. You're only modeling P of Y given X. Right? If X is your input sentence, right? HMMs model P of Y comma X. So you can marginalize it out over the Y's and just model P of X, so you can just generate sentences. Yeah?
Wait, so with the trade-offs of using like a higher order like model, the computation time and overfitting?
Yeah, you need more model, you need more parameters, right? So instead of this being 2 parameters of this function, it would be 3. The probability, the score from this is the last 2 sequences I observed. What was the score of the next sequence I observed? So it's cubic in L instead of quadratic in L. And then if you arbitrary unstructured, it's exponential. Yeah, so CRFs and HMMs, they are very similar to each other. The only difference is the difference between naive Bayes and logistic regression. Okay, whoops. Last slide. Okay, so I guess we talked about this, same number of parameters as HMMs, but we focus all the model capacity on learning conditional distribution. Prediction via Viterbi, graded set via 4 backwards using a similar interpretation of the optimality condition, but the optimality condition doesn't have a closed form formula, so we do gradient descent. And so next lecture we'll talk about a more general formulation for CRFs, has a more concise notation, matches the logistic regression notation, which uses a weight factor, matches the course notes that are released later this week, and is easy to reason about for implementation purposes, such as for the homework. And then I'll close next lecture with a small discussion on more general structure prediction problems. That's it. Sorry, no recitation this week.